Hello, everyone. I'm excited to introduce Pablo Barceló, who's the director of the Institute for Mathematical and Computational Engineering at the Universidad Católica de Chile. And Pablo's research interests are in database theory and also in the applications of logic and automata to databases, it seems. But today he's going to be talking about something closer to neural nets. So this paper or series of papers about analyzing attention and transformers and showing their Turing completeness. So this is, I think, mainly focused on a JMLR paper from 2021, but there's also some other related papers. So yeah, I'm excited to hear more.
Thanks very much for the introduction. Thanks very much for the invitation. And sorry to have missed the previous the previous talk. There was a problem with the schedule. Yeah. So yeah. In fact, 3 years ago we started working in this problem. 3-4 years ago, and this was my entry point to. As I was describing before, my entry point to the analysis of the expressive power of different neural network architectures. Yeah. So let me start by explaining what we understand by some basic notions here, like sec-to-sec neural networks and sec-to-sec sequence-to-sequence language recognizers. So the idea is to study neural networks that process sequences. Yeah. So we're gonna talk about sequence-to-sequence neural networks in which we have a sequence of numerical vectors of length n. Each one of them is composed by a d-dimensional vector of rational numbers. And from this sequence, we will produce another sequence, an output sequence y, of perhaps a different length, right? So this might be an input sequence of length n, and this might be an output sequence of length m. But the important thing is that these are composed by d-dimensional vectors numerical, which are numerical. So in general, these architectures require two things. They require a seed vector, which is a vector that allows us to start computing the output from X, and a stopping criterion. What is the stopping criterion? Is the length m of the output sequence y. So for how long are we gonna compute the output sequence y? So for us, a sequence-to-sequence neural network architecture will be a function n that takes as input an input sequence x, a seed vector s, and a stopping criterion m, and it computes deterministically an output sequence y sub 1 through y sub n. Yeah. So this is what a sequence-to-sequence neural network architecture will be for us. But of course, we want these neural network architectures to be able to recognize finite words, right? And that's how we come to the idea of having sequence-to-sequence language recognizers. So what is a sequence-to-sequence language recognizer in our work? Well, it's a tuple A that consists of a finite alphabet sigma, an embedding function f, a sequence-to-sequence neural network n, a seed vector s, and a distinguished set of final vectors. Yeah. So the idea is that we are, with this language recognizer, we are processing finite words over this finite alphabet, sigma, in such a way that the embedding function takes symbols from this alphabet and turns them into the numerical space. Then it's processed through the sequence-to-sequence neural network, starting from the seed vector S and checking for checking whether the last symbol produced, I'll explain this more carefully later, but checking whether the last symbol produced as a vector, as a numerical vector, belongs to this distinguished set of final vectors, right? So we will say that this sequence-to-sequence language recognizer accepts a word W over the finite alphabet sigma if the sequence-to-sequence neural network N, when given the embedding of this word, the input seed S, N, and M, yeah, we want to know whether for some M, the output word produced satisfies that the last symbol belongs to the final set of vectors, the distinguished final set of vectors. Yeah. Please stop me at any moment. Yeah. So
thank you.
Yeah.
I have a question.
Yeah.
The output sequence that is produced, does it only begin to be produced after reading the entire input sequence in this language recognizer?
Well, there is no, at this point, this is just a function. So there is no procedural way to understand it until we have a concrete architecture, no? And we will have one that is the transformer, and we will briefly talk about recurrent neural networks, but for the time being, it's just a function, right? And it's so we will say that this function, that this sequence-to-sequence language recognizer accepts this word if the output of this satisfies that the last symbol is in F. That's it, right? So later we will make this function be dependent on a particular procedural procedure, no?
I have a related question.
Thanks.
Yeah, please go ahead.
So does this F set have to be finite, or could it be an infinite set and we have some procedure for checking membership in it?
You mean the set, the function F, or this set?
The set of final vectors.
This set is infinite.
Okay.
Yeah, in general, for the Turing completeness proofs is infinite, but we have actually a polynomial way to check whether a concrete vector belongs to F or not.
Okay.
And this is part of the restrictions that we have to impose so that the problem doesn't trivialize. No?
Right.
Yes. So what is the language accepted by this sequence-to-sequence language recognizer? Is the set of all finite words W that are accepted by the sequence-to-sequence language recognizer, right? So such that for some M, the output is a sequence such that its final vector belongs to F. And so we are going to impose some restrictions so that the problems that we are studying do not trivialize, no? The first thing is that the embedding function can be computed in polynomial time. So given the word A in sigma, this will generate f of A as a numerical vector of dimension D in polynomial time. And the other thing is that we can check in polynomial time whether a set belongs to the, a numerical vector belongs to the set of final vectors. Yeah? So I will assume, of course, that familiarity with the notion of computability, Turing machines, and so on. So I will briefly describe what it means for a family of sequence-to-sequence language recognizers to be Turing complete. Yeah? So this family N will be Turing complete if every Turing machine, if for every Turing machine M, there is a sequence-to-sequence language recognizer A in N for which the language of finite words accepted by A is exactly the same than the language of words accepted by M. Yeah. So for every Turing machine, we can find an equivalent sequence-to-sequence language recognizer. Yeah. And notice here that the embedding function actually can be dependent on the machine. This is not the case for our Turing completeness result. This is very uniform, the way in which you obtain these embedding functions. But in general, you could have a different embedding function for each Turing machine. Yeah. So what is a classical Turing completeness result in this scenario? Well, the classical Turing completeness result is the one that tells us that encoder, decoder, recurrent neural networks, or RNNs, are Turing complete. So what's the idea here? You're given an input X formed by d-dimensional vectors, and with an encoder, you will compute n new vectors, h sub I. I'll show a graphical representation of this later, in a way that it depends on the input x sub I. Each h sub I depends on the ith vector in the input x sub I, and it also depends on the previous computed vector h sub I minus 1. And from then on, I will start computing from h sub n, the last vector computed by my encoding. I will start computing vectors g sub I up to g sub n that depend on the previous g sub I and depend on some output y sub I minus 1, that it's actually a linear transformation of the g sub i's. So how does this look like? Here we are given our input, x1 through x sub n. Yeah? We have an initial vector, h sub 0, that we declare to be 0. And from h sub 0 and x sub 1, we will compute a new vector, h1. From h1 and x2, we will compute a new vector, h sub 2, and so on, until we will compute the final vector, h sub n, recursively. And then we will combine our vector h sub n with our seed vector y sub 0, yeah, to compute g1. And from g1, we will start computing recursively g2 that depends on g1 and a linear transformation of g1 that we call y1. Then we have g2, and we compute g3 by using g2 and a linear combination of g2 that is we call y2. Yeah. And finally, we are interested in this output that is y sub n, which is a linear transformation of the last vector that we produce, which is g sub n. Yeah. So that's how encoder, decoder, recurrent neural networks work. And yeah, so there is a question here. It can be in general. For the Turing completeness result, it doesn't really need to be anything. It can be the identity. Yeah. So I'll mention this. I'll mention this here. So the classical result by Siegelman and Sontag says that the class of encoder, decoder, RNNs is Turing complete. That is, for every Turing machine, one can construct, in this case, it's a constructive reduction. One can construct an encoder-decoder recurrent neural network that accepts exactly the same set of words. And this Turing completeness holds even when R here is the zero matrix, that is, sorry, so we don't even pass this thing here, there are no biases. B1 and B2 are 0. O is the identity function. Yeah, so this, well, we are not passing this, so it can be the identity function. And sigma 1 and sigma 2 are piecewise linear sigmoidals. Yeah, so this is kind of the most restrictive version of this Turing completeness result. Yeah, so the Turing completeness is really based on the fact that we can compute these vectors G sub I for arbitrarily many steps, and this is encoding the computation of a Turing machine, essentially. That's it. Okay, so let me hopefully briefly explain what transformers are. Of course, this is abstracting away from many of the features that transformers have. We have tried to somehow formalize and clean up and try to identify the basic properties of transformers that ensure the Turing completeness. No? And later I will talk a bit about this. So transformers are based on the so-called attention mechanism. Yeah. So how the attention mechanism is formalized, at least in our papers, is as follows. You have a score function that takes two-dimensional vectors and computes a similarity score. It tells us how much these two vectors look alike. Yeah? And then you have a normalization function, rho, that takes an n-dimensional vector and produces another n-dimensional vector that in a way normalizes this vector by doing by ensuring that the sum of the feature values in this vector is 1. Yeah? So how this, once you have this score function and this normalization function, how the attention is defined? The attention takes 3 parameters. It takes a query, it takes a set of keys, well, in this case, a vector of keys, and a vector of values. Yeah? So first of all, we will measure the similarity of the query queue with each key k sub I. For each one of them, we will measure the similarity with our score vector. We will compute this with our score function. Then we will compute this score vector and we will normalize it with our normalization function. And once we have this vector that tells us what is the importance of each feature in the set of values for the query queue, yeah, the level of importance of each one of these features, we will define A to be a linear combination, well, in this case, a convex combination of the B sub i's in such a way that each S sub I is the value of the importance that we have assigned to this feature. This is what the attention of the query queue to the set of or to the vector of keys K with respect to the set of values B is doing. Yeah. So I hope that that this is more or less clear. If you have questions, just stop me at any point, and I'll be happy to explain. So for our results, which score function we will be using? Well, we will be using the dot product, but we will always be taking the negative value of the dot product. Yeah, so we'll take the absolute value of the dot product and we will take the negative value of that. Yeah? And for normalization, we will be considering the hard max function. what is the hardmax function? So the hardmax function signals in a vector the places where the max element appears. For instance, in this case, the max element appears here, here, and here. It puts a 1 on each one of them and then divides it by the number of times this max function appears in the vector. Yeah. So in this case, it will be 1/3 here, 1/3 here, 1/3 here. Yeah. So for our results, using this hardmax function is essential. It's an interesting question whether the same results can be achieved with, say, softmax, but we didn't dig into that. Yeah, but it's definitely interesting to consider other normalization functions, other score functions, and ideally as well to get general results telling you if you have this family of score functions, this family of normalization functions, then Turing completeness can also be achieved. Yeah. Okay, so this is where the ugly stuff starts, but I'll try to explain this carefully. So, what is an encoder layer? We take our input x1 to x sub n. These are vectors, right? D-dimensional numerical vectors. And we will have an encoder layer here that does the following. It takes a transformation, say with a feed-forward neural network, Q, another one K, and another one B, of each one of each one of these elements. So we will take as query for our attention layer. We will take as query a transformation of this x sub I. We will take as keys a transformation K of all these vector, yeah, vector of vectors. And we will take as values a transformation of all these vectors. And we will compute for each one of them a new vector a sub I that describes or combines the importance that this key gives to each one of these elements, and we will put it here. And later on, we will take another transformation O that takes this A sub I and produces Z sub I. And we will produce Z1 through Z sub n, which will be the output of this encoder layer. But something very important here, and which is in fact crucial for our results, is that you also have residual connections. Yes. So this A sub n here will not just be the output of this encoder layer here, but it will be the output of the layer plus the x sub I that comes from here. Yeah, and here you will have as output not just the transformation of A sub n, you will have the transformation of A sub n plus plus whatever you had here. Yeah, plus the A sub n. Yes. So our results use these residual connections in a crucial way. We need them. Yeah, and as I will mention later, we don't know whether they are essential to obtain the result. Yeah? And this is an interesting point because residual connections are used in practice. They were introduced, and probably they were introduced for a good practical reason. And this practical reason then transferred to a theoretical explanation of the Turing completeness, at least for our results. Good. So what is the encoder of a transformer? It's just the sequence of encoder layers. Yeah, we have L encoder layers. For our results, this concatenation of encoder layers is not necessarily, it suffices to have one encoder layer, but in general, this architecture allows for a stack of different encoder layers. Yeah? Do you have any questions so far? I know that my drawings are not particularly beautiful, but I hope that they are clear. And if not, I can explain things more carefully. Yeah, this is the worst slide. I tried to do my best, but truly the model is a bit ugly at this point. Yeah. So how a decoder layer works? So the decoder is computing an output y sub 0 to y sub n. So we have computed this inductively, and we want to compute the next symbol, y sub n plus 1. How are we going to do it? Well, first of all, we will do one layer of self-attention over the y sub j's that we have already computed. So as we did in the encoder, we will consider the attention that each one of these keys gives to, in this case, the input formed by the first I elements of the output. Yeah. And from this, we will obtain an output P sub I for each I by summing the output of this with the Y sub I. So we will have residual connections at this stage as well. And then it's when the decoder uses the encoder, because up to this point, they are completely separate. So what it will do now is it will do another call of attention to some external keys and values produced by the output of the encoder. So this was the output of the encoder. We will have a layer here that produces keys and values from this. And at this point, the decoder will make an attention to the encoder, whatever it was here, and it will output a new thing. And this thing will be summed to whatever I had before. And finally, I'll do another layer of transformations here, and I will add the A sub i's to this to obtain the final output of this decoder layer. But the decoder is not just one decoder layer, but it's a stack of decoder layers. And the new symbol y sub n plus 1 is produced by this last symbol here by taking a final transformation. Yeah. So you may wonder, why not just produce this instead of producing all this? But the fact is that this, given the way in which attention works, depends on all previous input. Now, this seems complicated, but it can all be done in parallel, right? That's a nice thing of the transformer. Each one of these things can be computed in parallel if you have access to this and the output of the encoder. If you have this, you can do it in parallel, and you will produce this new symbol here. Yes? Okay. So is that clear? I hope so. So what a transformer network will be for us, we will have as input a sequence x sub 1, x sub n. We will have a seed vector S that will act as y0, the initial symbol in the output. And we will have a value, stopping criterion m, and we will produce, with this idea of producing new symbols here, the complete output y sub 1 to y sub n. So before talking about the Turing completeness, let me talk about the limitations on expressive power that this model has as it is right now. So to obtain Turing completeness, we will have to extend this transformer network, because as it is now, it has a serious limitation in terms of its expressive power. So let us say that for a word W in sigma star and a symbol A, we will define the ratio of the symbol A with respect to the word W as the number of A's in W divided by the length of W. So this is the ratio of occurrences of A in the word W. So given a W, a finite word W, we will define the ratio invariant set of words, the set of words that are ratio invariant with respect to W as the set of all use, the set of all words use, such that for each symbol A, the ratio of A in U equals the ratio of A in W. Yeah. So what it can be shown is that transformer networks, as they are ratio invariant. That is, if a transformer, say, accepts a word W, it will accept every other word that is ratio invariant with respect to W. Yeah? Or say it a bit differently, the output of the transformer on a word W, yes, is the same than the output of the transformer on each word U that is ratio invariant with respect to W. Yeah? Because the transformer as it is, it's only taking into consideration the number of appearances of words, of symbols, more than the real order in which these symbols appear in the word. Yeah? So this tells us that transformers, in their original definition, are not even capable to capture all regular languages. There is no transformer network that accepts the regular language even sub-A that consists of all words that have an even number of A's. And why is that? Because the transformer network cannot distinguish between the word AABB that has an even number of A's and the word AAABBB that has an odd number of A's. Yeah. So, as we said, the reason for this limitation in expressive power is because the transformer doesn't have access to the order in which the symbols of the input are provided. Yeah. And this limitation has been recognized in practice by several papers in the way in which it has been tackled is by providing positional encodings. Yeah? Knowledge about the position in which one symbol appears in the input word. Yeah? So what is the idea here? So the idea is that a positional encoding extends the embedding function f that takes a symbol and produces a numerical vector that represents it. It will extend this with information about the order of the word. So it will take an extra embedding function f sub position, which takes a position and computes a representation of this position. So hence, transformer networks now receive not only sequences of this form representing a finite word via the embedding function, but it will take the embedding function plus the positional encoding. So it will take the embedding function of the first symbol plus the positional encoding of the first position. The embedding function of the embedding value of the second symbol plus the positional encoding of the second position, and so on. Yeah? That's the idea. So we will have complete knowledge about the order in which these symbols are given in the input. And in this way, with these positional encodings, we can obtain Turing completeness for the class of transformers. So the class of transformer networks with positional encodings, and in fact, positional encodings of a very simple kind we can discuss about later, is Turing complete. And indeed, this holds even if transformer networks have a single encoder layer, as I said, and 3 decoder layers. So a finite number, a fixed number of decoder layers. Probably it can be done with 2 as well, but the way in which we did it required 3 decoder layers.
I have a question about the positional encodings.
Yeah.
So these are mapping from like the natural numbers into a finite dimensional vector space. So
with infinite precision, no?
With infinite precision. That makes sense. Yeah, I see.
Yeah. So infinite precision is required here. Otherwise, you don't get Turing completeness. In fact, by bounding the precision, you can get different complexity classes, right? So the precision, limiting the precision would give you different complexity classes if you want. Mm. So the proof idea is quite simple. What we really want to do is to encode the computation of a Turing machine on the input. So we are giving this input A1 to A7, and we will use the following sequences. Q to the I, that tells us the state in step I of the computation of the Turing machine. S sub I, that tells us what is the symbol read in step I of the computation. BI, which tells us the symbol written in step I of the computation. MI, which tells us the direction in which the head moves in step I of the computation. And CI, which shows what is the cell visited in step I of the computation. So this is all the information that we require to have in our decoder in order to mimic the computation of a Turing machine. Yes?
By cell, do you mean the position on the ribbon?
In the tape, yes.
Okay, thanks.
So it will be a number, right? Cell number 16. Yeah?
Thank you.
Mm-hmm. Okay, so graphically, this is the idea of the proof. So in the encoder, which is here, we will have access to the input. Yeah, so we will be reading the input. And this is what the encoder does. The encoder essentially just tells us what is written initially in the ith cell of the tape. Yeah. And then the decoder will start computing the computation history, or will keep the computation history of the Turing machine on this input. So this is the symbol that we want to output. This is what interests us, is the state in which the machine is in step T, together with the symbol it's reading. So if at some point this represents a final state of the Turing machine, we will say that this is a final state of our transformer. Yeah? And we can recognize that quickly in polynomial time. So what the decoder will do? The first thing that it's easy is that it will compute the transition function. So in state q sub t, or q to the t, reading symbol st, it will move, applying the transition function, to the next state, q t plus 1. This is what it will write. We know that from the transition function. And it will move left or right. This is just a 1 or a minus 1. Yeah? This is easy to implement because we just look at the transition function from the Turing machine. But what we want to do is to compute the symbol once we move in this direction, right? Which symbol we have under the head of the Turing machine once we move in this direction. And this, of course, depends on all the history that I have here. But the way in which we do that is by taking advantage of the attention mechanism. So first of all, we want to compute in which cell of the tape in which cell of the tape the head of the Turing machine is in step t plus 1. How are we gonna do that? Well, this is encoded in all these ones and minus ones here, right? So if I sum over all the m sub i's, yeah, if I sum over all of them, this will give me precisely this cell here. And how do we sum? Well, we can take advantage of the attention mechanism, yeah, to give the same level of attention to each one of these, and then we will compute some average that will allow us to compute the cell number. So this tells us that we are in this cell in step t plus 1. Yeah, I know in which state I am, I know what did I write before, and I know in which cell I'm reading. But I want to see which symbol do I have there, no? And the symbol depends on the symbol I wrote, the last time I visited the same cell, no? Which might be very far away in the past. But how do I do it? Again, by the attention mechanism. We have designed the attention mechanism in such a way that it maximizes, it takes a maximal value exactly in the place, over the last place in which this cell was overridden. And if we have never visited this cell, we will also know it, and we will know that the symbol being read there is a blank symbol, no? This is what it's telling us. So we will perform attention, we will look at the last place in which this cell was overridden, and we will bring the symbol from here to here, and this is the symbol we are reading in step t plus 1. So we can bring this here and continue the computation. Yeah, so that's the very general idea. As I have said, the details are cumbersome and ugly because the way in which these transformers work, but there is nothing difficult behind this, right? It's a very non-mysterious proof in that respect. So to finish, I would just like to mention one open problem about which I thought for a while and I couldn't find an answer, and I would be happy to see what's the answer to this. Are residual connections essential for Turing completeness? We don't know. Yeah. So it's interesting that these residual connections that seem to have been introduced for a practical reason turned out to be important for our Turing completeness result. But we don't know whether they are essential. Yes. So and I think that this is an interesting question because to have a more minimal architecture that achieves Turing completeness is a meaningful problem, no? If you could get rid of residual connections, then you would have less things to learn, less features in your architecture, and it might be simpler to learn, to train, to generalize. It could generalize better without losing expressive power, no? And that would be the idea. Yeah, so thanks a lot. This is what I wanted to present, and if there are questions, I'm happy to take them. Thank you.
Thanks, that was great.
So
were you familiar with this architecture of the transformer in general? All these residual connections and so on?
I don't know if I speak for everyone here, but I think a fair amount of us are familiar with transformer architectures. Did you consider layer norms?
No. No. No, this is one of the things that we didn't consider, and it could be considered. There are so many things that could be considered here, no? But no, yeah.
No, that's very fair that you didn't. Just wanted to check. No. You said something that sort of caught my attention because it was something that I played with a lot. In order to figure out where you were on the tape, you summed all of the choices to go left or right or stay. And I imagine, because of course, technically the transformer only allows you to average. So yes. You had to actually then multiply that average by your current position in order to... Yes, indeed. Okay. Indeed, that's what we do, yes. Okay. So there's some assumptions on the strength of the feed-forward networks as well. Absolutely. But yeah, this is where all these ugly parts come. This is what you have to do with these feed-forward networks. Yeah. Mm-hmm. No, it's very fair assumptions. I think so. Yes. We didn't try to cheat ourselves, at least. We really wanted to. We really wanted to understand what were the minimal requirements for this architecture to be fairly Turing complete. Yeah. Now, the only thing that puzzles me a bit is this hard max function, no? Because it would be much more fair to use something like softmax. But then it's at the expense of having a much more complicated result as well, no? But it's definitely something in which is interesting to look at. Well, you are in the presence of several people who used hardmax. Really? Okay.
Yeah. So I mean, I've been working on analyzing, I guess, like not this kind of encoder-decoder setup of transformers, but transformers with an encoder and then like a classifier on top. And there we had one paper about hardmax transformers and one about the softmax transformers. And so far we haven't been able to separate them. We have kind of the same upper bound for both. But yeah, I think it's super interesting to figure out if there's a difference or not.
Well, my conjecture would be that nothing changes here, at least in terms of Turing completeness, if you keep if you replace hardmax by softmax, no?
Right.
But the proof might be a bit more difficult.
Yeah, that makes sense to me because the softmax seems, in some sense, just more general, because you can always kind of approximate a hardmax at least with the softmax.
Yes. Yes.
I had a question about your when you were talking about the precision of the positional encodings, and you said that you can get different complexity classes if you constrain the precision? Could you say more about that?
It was on the paper.
Okay.
I don't remember much what we did. So the paper over here. So let me. Yeah, so the idea was that for every language L that belongs to, say, deterministic time of Tn, so take the class, the complexity class deterministic time of Tn, you can construct a sequence-to-sequence language recognizer A that accepts this with a precision of at most log of T bits. That's the idea. Yeah. But it was a bit more technical than that. But the idea that was that for each one of these classes, you can bound the amount of precision that you need to capture this class. Yeah?
That's cool. I think I'll check that out.
So thanks for a very nice talk. I was curious about the positional embedding that you used in your results.
Which kind of positional embedding we use?
Correct.
Yes, it's yeah. We have to have, for position I, we have to have I plus 1, 1 over I plus 1, and 1 over I plus 1 squared. Yeah, that's what we needed. Don't ask me why, I don't remember. But yes, so we require 3 different ways in which to encode the position.
Mm-hmm. Did you consider using angular, basically polar representations?
No.
Because they're easier to compare using inner product.
You're right. No, I don't really remember well why, but you're right.
Mm-hmm.
Yes. That might be something interesting to take a look at, whether this simplifies things somehow. Yeah, at the expense of having a more complicated positional encoding, a bit more complicated. Yeah.
I was just searching after you mentioned that you are using this hard max and wondering if it's necessary. And my vague memory, and I'm looking now and I'm not sure, but I think in the paper R transformers universal approximators, they also replace the softmax with a hardmax.
Okay.
And it's possible that they rely on this in order to obtain their results. I'm not sure if it's only for some of the lemmas or for the ultimate major result, but it appears for some stuff.
Okay.
I'm not sure.
Mm-hmm.